first we put equals. Good.
I got this one.
All right, we want miles. Now what do we do? Given information. 2, 4, 3, 7, 0, 0, 0 inches. Times, because inches are not miles, inches in the denominator, or inches on the bottom, and miles on top. But I don't know that conversion, so I would go into feet. Okay. How many people know that conversion? 2 people knew that conversion. Wow. Okay, that might explain some of our problems. Okay. You should review some of your conversions, and remember that you should write these down on your note card if you don't remember them. Okay. So for the 2 people that did know that, what is that conversion? 1 foot is 12 inches. Is feet the same thing as miles? No, so what do you have to do? We have to do another conversion. Ideally, we'd go feet into miles, right? Feet in the denominator so that it cancels miles in the numerator. Does that conversion exist? It does. You were saying yards. You know how to convert yards into miles? You know that one? Do you know that one?
Used to, I don't know.
Oh, okay. I mean, that's okay if you did. I was just surprised. The only reason I know this one is because I saw some stupid internet meme about tomatoes.
Wait, what was it?
So the answer is 5,280. So 2 8 O's. So if you remember 5 tomatoes, you have your conversion between feet and miles. Yeah, insanely dumb. But the entire imperial system is horrendously horrible. Okay? So that would be our conversion. Then our feet cancel, and we'd have our miles. So this isn't a process of, oh, I need to divide by 12, multiply by, or divide by 5,280. I set up the unit systems to allow me to do the conversion. That's why they're there. And at each stage, I had to ask myself, do I know that conversion? Okay? Do I know it, or can I know where to look it up? Okay? That is part of our process. A lot of people don't like the mathematics. Okay? And so that's what this little question was supposed to ask. Notice the font size is really, really tiny. Any ideas why the font size is really, really tiny? Because to provide the answer to this quiz question, the font size has to be really, really tiny. Okay? So, and that's usually the response. Goddamn science, it's science's fault. That is not science. What we just had up on the slideshow, that calculation, that was science. Science just cleaned the hell out of the English. Science trumps English here. It's a process of organization and simplification so that to solve this question, we don't have to launch into something that is this horrendously horrible. Okay? Note, within this, there's a part that's in italics. So I did this in another class where I had an English teacher as a partner. And he said that my explanation without italics was not sufficient. That I needed an explanation at the beginning. Hence, I had to add the stuff in italics. Okay? This is the exact same solve that was just on the slide. Okay? What we are trying to go through and do is something like this. So when you ask me to explain a conversion, this is what I'm trying to tell you. Okay? Focus not so much on the words, but what is the process? Where am I placing things within those images? Okay? A picture is worth 1,000 words, almost quite literally. Okay? Yeah.
It's kind of just like proofs in geometry.
It's kind of like proofs in geometry. Okay? We set up with certain rules that allow us to make conclusions. Right? And it simplifies what we have to go through and do and think about and ultimately read. right? So every time we go through and look at something in chemistry, we're using a symbology to represent a crap ton of text, right? The part that's tricky is that you have to be processing the symbology and tying it back to all that text, right? But that text all has to happen in your head, right? So try to simplify your images down. Think about what those things mean, because what they mean is the text, right? So when we move into chapter 9, we're now looking at chemical equations. Well, what does a chemical equation mean? It's a recipe. It's how do we put something together. That's all it is. The reason why chemical equations now become so tricky and everybody goes, oh my God, I can't do chemistry, is that when you think about a recipe and it asks for a cup of flour, what can you do? You can physically grab a cup of flour. That's pretty easy. If we look at a chemical equation and it asks for 1 molecule of hydrogen, what do? Not grab it. You have no way to grab it. You have no physical contact with it. It's this kind of nebulous idea that we're then saying you just have to process. Okay? It's the same concept as a recipe. It's the same concept as instructions for making anything. Okay? We're just dealing with things down on a symbolic level. We have to think about it at a symbolic level, because you don't want to think about it on the real level, because we can't fathom that. Right? The other analogy that we can use in that process of fathoming, how many people are concerned about our national debt? It's only 21 trillion. Like, that's only 15 numbers lower than me. I'm 36, 21 trillion. That's not a big difference. It's not 21 trillion, it's 21 0 0 0 0 0 0 0 0 0, and I think I need another set. 0 0 0. Okay? That number is now so massively huge our brains can't comprehend it. Right? So what did we do to make it a little bit more understandable, or at least shrink it down? We, instead of saying all of those zeros, listed it as trillion. When I think about a mole, what is the point of a mole? Well, it's that 6.022 times 10 to the 23rd, or 6.022 0 0 0 0 0 0 0 0 0 0 0 0 0 0 zeros, a lot more zeros. Right? That number is so incomprehensible that we can't manipulate it easily. So we just invented a system, a new unit that says, well, I don't want to deal with that massive number. Instead of dealing with that massive number, I'm just going to call it a mole. We did the exact same thing with money. A trillion has a bunch of zeros in it. I can't deal with those zeros, so I'm going to turn all of those zeros into the word trillion. It simplifies my thought process. It simplifies my calculation. I still have to do that conversion to do an interpretation of it. Okay? So you have to be constantly thinking about how to go about that conversion. Okay? So let's pick something for a formula. Okay? Here's a compound. What is that compound? The picture is a compound. What is that compound? It's a wheel. Okay, we're not making it difficult. Start easy. What things made that wheel? Okay. Be a little bit more specific than rubber. We have the tire. We have the spokes. We have the rim. Okay. We have the hub. We've got the tubes on the inside. We've got all of these components that go into making that a wheel. Okay. And we could list out all of those components. But it would be a bit tedious to write all of those things out, right? Spokes. Okay, 1 tire. 1 tube. Okay? Lots and lots of words that would go with this. So what do? We abbreviate. Instead of writing it as spokes, I might write it as SP. Instead of writing it as tires, I might write it as TI. Tube, TU. Okay? It simplifies the amount of stuff that I have to write out for it. Okay? If we go through all of that, all of those together, that's supposed to be one of those ellipsy things. Okay? It's supposed to make what? Well, one wheel. Well, how might we abbreviate wheel? We might just go WH. This is a reasonable system because we can physically grab a hold of these things. We recognize those differences. But if we can't physically grab a hold of those, I don't know that a wheel is something, what makes up the wheel. Right? So in chemistry, I don't want to use a new symbol for multiple pieces or multiple new things. So instead, I come up with the abbreviation for my formula, where it would be spokes, 32, tires, 1, tubes, 1, and I now have a chemical formula. That chemical formula is the recipe. It tells me what things go into that compound. Right? That's what it means. It is a chemical equation. Right? The thing that's powerful behind this is I can then take those mini recipes and I can combine them with other recipes to make new things. Like I can take this tire and I could combine it with, that was supposed to step differently, a frame to make a bicycle. How many of those wheels would I need to combine with that frame?
2.
I need 2. So I could write it out in this drawing, but again, that now seems a bit redundant. Could I simplify it? Say 2 wheels. Okay. We've simplified our notation, implying some meaning behind it. We're doing some mathematics, albeit relatively simple mathematics, to make those applications move through. What can we now do with this recipe? Okay. I know someone that built 4 bikes. How many wheels did they use to make those 4 bikes? How'd you do that? You did all that calculation in your head, so now stop, write it down. Write down the calculation that you did in your head. And what are you saying? Well, it's just 4 times 2. Knock it off. Set up the conversion. Okay? You're tracking your units. What are you solving for? Wheels. What are you starting with? Bikes. 4 bikes becomes how many wheels? How do we solve it? Everybody agree? Where did I get the 2 and 1 from? From the chemical equation that tells me I need 2 wheels to make 1 bike. I'm using the number in front. How many frames were needed?
1.
To make 4 bikes?
Oh, no, for individual bikes, 4 bikes before.
Okay. When I bring in a new question or a new solve, I have to do a new equation. I now have to convert those bikes into frames. How do I do that conversion? Well, bikes, frames. Where do I find the conversion factor between bikes and frames? From my recipe, the chemical equation that tells me it. And in that chemical equation, where does it tell me the number of frames I need? There's an implied 1. What's in front of the bike? An implied 1. Because you can physically see and manipulate these things, you've internalized that numerical information. What a chemical equation does is it removes that ability to internalize. You have to interpret the equation. We are forcing you to do so. If you do not do so, that's when you make grievous errors in your calculations. And you start trying to just multiply or divide by random numbers. If you're lucky, it works. If you're not lucky, it doesn't. This is why you need to understand what these things mean. Okay? So 1 frame, 1 bike. Okay? 6 wheels and 3 frames. How many bikes can you make?
3. Wait, 6 wheels, you said?
6 wheels and 3 frames. I can only make 3. Okay? And if I did that, I would use up all of the parts. Okay, what you're doing is internalize the 6 wheels, converting it into bikes would be 3 bikes. 3 frames would be 3 bikes. Those numbers are the same. 3 is my answer. What if I give you just 2 wheels? How many bikes can you make? This is a nebulous question. Doesn't give you enough context to really apply what's going on here. It says given just 2 wheels, how many bikes can you make? If you only have 2 wheels, how many bikes can you make? None. Okay? The question hasn't clearly stated, do we have any frames or not? So if you had a question like that, we have to be a little bit careful with it. Okay? Sometimes chemistry will phrase questions like that, implying that there's enough frames. Okay? Sometimes not. So you have to be careful with that wording. I do try and watch out for that wording when it comes to exams, but if at any point you question it, ask. Okay? Given 3 wheels and 2 frames, how many bikes can you make? Okay? How did you come up with 1? If I have 2 frames, I would make 2 bikes. I don't have enough wheels to support that. So what I'm doing is running these simultaneous calculations and seeing how much could be produced out of it. Well, wouldn't 3 wheels produce 1.5 bikes? Can I have half a bike? No. No. That's not in our realm. We aren't allowed to have half of a unit. The same thing happens with chemistry. We can't have half of an atom. But what if I scaled that up to 3,000 wheels and 2 frames? Or sorry, not 2 frames, 2,000 frames. Okay. Well, now it becomes 1,500 bikes. Could I have 1,500 bikes? That becomes more reasonable. Okay? So when we're dealing with these issues of scale, when we think of a chemical equation, we typically think of it in very small numbers, single units. Okay? Chemistry can't function at single units. Why can't it function at single units? What are the pieces in chemistry? What is the smallest indivisible, well, not indivisible, what is the smallest piece that we use to make something? An atom. Okay? Can I grab an atom? No. So if I can't work with it at an atom level, the equation kind of loses its meaning until I scale the equation up to an amount that I can get a hold of. Instead of grabbing 1 atom, I'll grab 6.022 times 10 to the 23rd atoms. That larger number of atoms is now something I can get a hold of. I can put that in a bag, and I can make that bag react with another bag of stuff. Okay? So scaling it up is what helps us get through and solve these things. Last question on this one. We'll probably see this slide again. 40 grams of wheels and 15 pounds of frames. How many bikes can be made? Why can't you readily tell? What does our chemical equation tell us? The number of these things. It's a count. Our measurement is a count of each of those pieces. What is the measurement of grams? Mass. Mass and count are different measurement systems. I have to do a conversion from mass into counts so that I can get or use the equation. The equation is only useful if I'm in a count type unit. Kind of make sense? So the count type unit with bikes and frames is relatively easy because we can just see it as a piece. Okay? A wheel is a piece. A frame is a piece. What is our piece in chemistry? Atoms. Right? But the only thing we can react is two atoms. Mole is the unit, the measurement on it. I'm asking for the substance. What is the piece? What is water? A molecule. Does water react with things? Yes. So it's not just atoms that react in chemistry, it's also molecules. So if I'm in a unit of atoms or molecules, that is now a count unit. I can scale that up to moles. Right? And that's where the mole unit comes in. Kind of make sense? So, when we now switch it to a chemical equation, I know this looks a bit daunting, so let's erase some of that and just come up with what we see first. Okay. What does that equation mean to you? Nothing is a perfectly valid answer. Does that mean nothing to somebody in here?
No.
No. Okay. Fair enough. What does it mean? Just nitrogen, oxygen?
Nitrogen dioxide.
Okay. So now we're starting to run into some nomenclature stuff. You're like, I don't know what that is. Just call it no. Say no. It's no. How many no? Two no's. Make it right. Ha, no. Ha, yeah. Two no's react with one O2, we can call it dioxide as well. Starting to get a little bit fancier with our terminology. Produce two notes. Right? Because two note. The silence is deafening. Nitrogen oxide. Okay, back to nomenclature. Nitrogen oxide, two nitrogen oxides react with one oxygen molecule. It's not dioxygen, it's just oxygen because it's a diatomic molecule. Become two nitrogen dioxygen. That's where or dioxide. Okay? 2 watts of NO. What is the measurement in this case? Molecule. I'm saying 2 molecules of nitrogen oxide react with atom. There's only one atom there? 1 molecule of oxygen to produce 2 molecules of nitrogen dioxide. So we've included now a unit behind it, okay, a measurement unit. That's our molecule unit. Okay, that works. That is a valid conversion. So what we're now saying is if we look at our fancy table here, 2 molecules of NO will react with 1 molecule of O2 to produce 2 molecules of NO2. I now have a conversion factor. I want to make 5 molecules. Let's not do 5 molecules. That's a bad number. Let's try that again. Let's just be extra creative. 8 molecules of NO2. Whoops. Yeah, I want to make 8 molecules of NO2. It's in a bad place. Let's not do that. How many molecules of NO2 can I make if I give you 8 molecules, of NO and enough O2? So what is enough? Okay? Enough means so much that I don't care what the number is. It's not going to affect my answer. Okay? How many molecules of NO2 can be produced? Okay? Well, what's my conversion factor? How do I convert molecules of NO into molecules of NO2? According to my chemical equation, what number shows up in front of molecules of NO2? 2. What number shows up in front of molecules of NO? 2. How many molecules of NO2 are produced? 8. The conversion factor allows me to work with this. I'm just pulling the numbers straight out of the chemical equation. All we've done is added that extra unit on it. That unit is implied in the chemical equation. You have to recognize that it's implied. Okay? Let's switch it up. New question. I want to figure out now what happens if I give you 1,000 molecules of O2. How many molecules of NO would I need to completely react with it? Right? So what's my solve? I'm trying to find molecules of NO. What am I given? 1,000 molecules of O2. Molecules of O2 needs to cancel. Molecules of NO needs to show up on top. What number shows up with molecules of NO? What molecule or number shows up with molecules of NO? 2. What number shows up with molecules of O2? 1. What's my answer? 2,000. How many molecules of NO2 would be produced? Okay. So now in my quick change, I want molecules of NO2 now. That means the number has to change here. And that this needs to be NO2. What number is tied to molecules of NO2? 2. What number is tied to molecules of O2? 1. Which means? $2,000 molecules. Yeah? Okay. Let's try another one, because you guys seem to be pretty good with those simple numbers. So let's move up to some, crazy numbers. Given 6.022 times 10 to the 23rd molecules of NO. How many molecules of O2 would need to react with it? Molecules of NO needs to disappear. I need molecules of O2 to appear. What number is tied to molecules of O2? 1 from the chemical equation. What number is tied to molecules of NO? 2. What do I do? Divide by 2, and the answer becomes? Oh, shoot. Of course I picked the wrong one. So let's ignore the numbers underneath. The answer would become 1/2 of that, which is 3.011, maybe, times 10 to the 23rd molecules of O2. How many molecules of NO2 would be produced? Well, now it's not O2 on top. I want NO2. 2 on top, which means my answer is 6.022 times 10 to the 23rd molecules of O2. Okay? That number is now so large, I can't manipulate that number very well. I wish I had another unit system that I could shift to that would allow me to understand that number or bring it down to something that didn't have to involve this stupid power of 10. Can I convert the unit of molecules of NO into some other unit system? How about moles? Because it was black. Notice at this point what I'm trying to change now is the measurement unit, not the substance. So notice the substance stays the same on both the top and the bottom. What is the conversion between molecules and moles? 6.022 times 10 to the 23rd molecules is 1 mole. How many moles of NO did I start with? 1. I took this crazy number, 6.022 times 10 to the 23rd, and I made it 1. Okay, 1 what? Mole of NO. I've taken a number that seems so daunting and ridiculous, 21, 0.00000000000, and turned it into 21 trillion. I did the same thing here. I took that 6.022 more zeros and turned it into 1. Why did I turn it into 1? I can understand the number 1 a lot better than I can understand the number 6 times 10 to the 23rd. Okay? I have 1 finger. I don't have 6 times 10 to the 23rd fingers. Okay? Which is a silly analogy, but that is literally what we're doing with our unit conversions. We invented new units so that we could deal with those numbers. We can deal with numbers 1 through 10 because we literally have 10 fingers. Okay? If we only had 3 fingers as an entire populace, okay? So not individuals, because individuals are still going to deal with the 10 system. If we only had 3 fingers, our entire numerical system is going to change. Okay? Because to get to 10, we would need 3 people. And to get 3 people together to agree on anything is never going to happen. Just look at the world around us. Okay? So all we're trying to do is make the world understandable. We first start with a chemical equation with units that we can't manipulate. So we scale them up to systems that we can manipulate, but that scale up created havoc because it made it even more difficult to understand. So we invented a new system that we could go through and use. Okay. Do I have to go from molecule up to this 10 to the 3rd to then get to moles? What was the number associated? Okay, so now we have to switch this up because I picked a bad example. If we scale to a new example, what if I start with instead 12.03 times 10 to the 23rd molecules of NO? If I go through my conversion factors, what am I going to find? Well, the O2 is going to be half that. 6.022 times 10 to the 23rd. The NO2 will be the same. If I convert those into moles, what do I get? 2 moles, 1 mole, 2 moles. We go back and we now compare the top line to the bottom line. Do I have to go through and deal with the whole molecule system? What number shows up in front of NO? 2. What is the measurement unit? Could be molecules. It can also be moles. Okay. The mole unit is more useful for me because that's the one I work with every day. That's what chemists function in because that scaled the world of atoms up to the world of humans that we can now manipulate and work with. Okay. So we don't have to worry about molecules anymore. We'll deal with much larger amounts in moles. That's the beauty of our chemical equations and the beauty of moles. Okay? So what can come out of that? We can get all sorts of relationships. So when we look at our balanced equation, okay, so this is a new equation. If I look at this balanced equation, I can get all sorts of conversion factors. I can convert nitrogen into nitrogen oxide. I can convert oxygen into nitrogen. Really? I'm allowed to convert oxygen to nitrogen? I can inhale oxygen and spit out nitrogen? No. If I follow the chemical equation, that chemical process, I can convert it. I need to use that recipe. Right? So I have to be following that chemical reaction. This isn't just meaning, oh, randomly at all times, oxygen can be converted into nitrogen. That's not the case. It's only through this chemical equation. Okay? What this sets us up with is this system. Right? And what we see down here looks daunting. These are all the possible conversion factors that could come out of that single chemical equation. This is why the chemical equation is cool, because we now have access to a whole bunch of different conversion systems. Okay? The chemical equation provides us that context. We have to do that interpretation. Okay? Kind of makes sense? Okay. So, do it. How many moles of oxygen react with 2.25 moles of nitrogen? Do you want to repeat that? We've got our step 1 and step 2 down. What needs to happen to the units of moles of nitrogen? It needs to disappear. It's not in my final answer. So it needs to cancel out. For it to cancel out, where must the moles of nitrogen show up in my conversion factor? On the bottom. Okay. What unit do I want to have show up? Moles of O2. Where do I find the conversion factor between those two substances? That's in the chemical equation. So if I look to the chemical equation, what number shows up in front of O2? 1. What number shows up in front of N2? N, you're right. And our answer becomes 2.25 moles of O2. Okay? We use the information we've got. I think that question was too easy. So let's switch this up. How many molecules of oxygen gas react with 2.25 moles of nitrogen? Okay, so we're going to go through and solve both ways. Because I walked around and I saw only one person do it one way, we'll do that way second. Okay? So to start it off with, because this part is consistent across both of them, I want molecules of O2. So I'm going to use the abbreviation MLCS for molecules, and there's my symbol for O2. What am I given to start with? 2.25 moles of nitrogen, which is also true for the bottom one, 2.25 moles of nitrogen. Okay? And right there is actually about as similar as they get, okay, ish. So we'll go ahead and just continue through with our conversions up top. So I noticed most people went through and said, okay, well, I want moles of N2 need to become molecules of O2. So the first thing we should acknowledge is what happened to the substance. It changed. What happened to the measurement unit? It changed. So I have two conversions that I have to address here. Okay? So this is why it's important to write down the measurement and the substance, because then you've got a hint on how many things you have to do. Okay? So if we go through and do this, what most people went through and did was wrote moles of N2 and then wrote molecules of O2. So, well, can I use Avogadro's number? No. Avogadro's number converts a count of one substance to a mole of that exact same substance. Okay? Avogadro's number converts the measurement, not the substance. And if we look at what conversion we've written out here, we're trying to convert, in what's written there, the substance and the measurement. I'm not allowed to do that. Okay? So what I saw most people do is say, okay, well, I can't convert to molecules of O2, so I'm going to convert to molecules of N2. Okay? Well, now I'm converting the same substance, so now I can use Avogadro's number, and I can write 6.022 times 10 to the 23rd molecules of N2 is 1 mole of N2. Now the numbers can come in. My units, moles of N2 cancel. I'd have molecules of N2. Is molecules of N2 what I want for an answer? No, so it needs to cancel. I place that in the denominator. What do I want in the numerator? Molecules of O2. Now the only unit that is changing here is the substance. Okay? Where do I find the conversion factor for a substance conversion? Not the formula. There was a reason why it's a slow pause there. We can sometimes convert substances through chemical formulas, but we're not converting it here. There is no formula that has nitrogen and oxygen in it. What has nitrogen and oxygen in it? The chemical equation. Okay, so we go to the chemical equation. What number shows up in front of molecules? 1. What number shows up in front of, molecules of O2 is 1. The number in front of molecules of N2, 1. What happens? Our units cancel and we're left with molecules of O2 and we'd have our answer. Okay? Perfectly valid. The other approach that someone took is they went through and looked at this and they said moles of N2 and I wanted molecules of O2. Ah, crap, I can't do that. But I can convert the substance as long as that's not molecules, as long as that is moles. Because my chemical equation gives me that also. It tells me 1 mole is 1 mole of N2. What happens? Moles of N2 cancel, and I'd have moles of O2. Is moles of O2 my answer? No. What has to happen? Moles of O2 on the bottom, and what do I want on top? Molecules of O2. Is that a valid conversion factor? I'm only converting the measurement unit. Is that measurement unit conversion allowed? Yes, that's Avogadro's number. It is 6.022 times 10 to the 23rd. Mathematically, we're doing the exact same thing. Unit-wise, we're doing something different. Okay? The end result is still the same. This is one of the reasons why I think students can get confused with conversions. Everybody sees a slightly different path. So if I go through and show one path, half the class is like, I get it. What's the other half of the class saying? I don't know why you did that. That didn't make any sense. Because you saw a different path. There's multiple paths through. There's multiple ways we can find those relationships. But you have to verify that it is indeed a valid relationship. Make sense? How are we feeling on this? Not bad. Some people are sleeping, so I'm going to guess that you got it. So, how many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? And because you guys are doing well, I'll give you 2 minutes. What are we solving for? Moles of CO2. What are we starting with? Moles of sodium hydrogen carbonate. Make sure you read the question carefully. Sodium hydrogen carbonate. That's 1 mole. Those are not the same thing, so I need to get rid of my units of moles of sodium hydrogen carbonate. And I need to get units of moles of CO2. Not changing the measurement, but I am changing the substance. Where do I find information about the substance? The chemical equation. What number is associated with CO2 in the chemical equation? 1. What number is associated with sodium hydrogen carbonate? 2. What happens? 1 divided by 2, my answer is a half a mole of CO2. Can I have a half a mole? Yes. I can't have half a molecule. I can have half a mole. Right? Because a mole is now a really large number. I can have half of a really large number. Okay? Kind of makes sense? So let's make it a little bit trickier. What is the mass in grams of sodium hydrogen carbonate when 2 moles of CO2 are consumed? We'll do the same thing, 2 minutes, and I'll offer extra credit. Okay, so in our first conversion, moles of CO2, ideally I would go into grams of sodium hydrogen carbonate, but that's 2 conversions in one step. So what do I want to convert to? Okay. I'm going to have to actually convert into moles of sodium hydrogen carbonate. Okay. And we'll draw the other example here in a second. Okay. So what is that conversion? 2 moles of sodium hydrogen carbonate is 1 mole of CO2. Those are the numbers coming from the chemical equation. Okay. Moles of sodium hydrogen carbonate is close to what I want for an answer, but it's not perfect. So I need to get rid of the units of moles. And ideally, what do I want? Grams of sodium hydrogen carbonate. Where do I find that conversion factor? That's adding up the masses on the periodic table. Right? Which was a little bit more work. Which the number was 84.01. Because sodium is 23, hydrogen's 1, carbon's 12, oxygen's 16. There's 3 oxygens. 48 plus 12 plus 1 plus 23 is 84. If you trust somebody else's calculator, not me. Okay. What if you had tried the conversion here, moles of CO2 into grams of CO2? Okay. Well, then what has to happen in the next step? Grams of CO2 must convert into grams of sodium hydrogen carbonate. Can I convert the substance through a mass unit? The substance is only allowed to be converted through a chemical equation. The units in chemical equations are counts, not mass. That second conversion is now invalid, which means my grams of CO2 conversion, not useful. Does that make sense? So when you do these, you will have multiple options. It spiders out. Try one. Move to the next conversion. Does that next conversion make sense? If it doesn't make sense, you have to backtrack and try and convert something else. Okay? Sorta, kinda? Sorta, kinda. Okay? So this question should look kind of familiar. We won't make it a quiz. Okay? We'll just kind of put it up there and let you worry about solving it later. So this question should look familiar because it was on the test. It was on exam 2. You saw all this stuff with moles and grams. You're like, what the hell? I don't know how to do any of that. Okay? You did in that first exam. You did know how to do those conversions because I gave you what those conversions were. If we look at what's found in each of those conversion systems, all of that information is stuff that you are now responsible for knowing. Okay? 1 mole of oxygen consumed, 2 moles of water are produced. Where do I find the relationship between oxygen and water? From a balanced chemical equation. So I would provide a little bit more context so that you could draw out the chemical equation. You could then balance it. You could then tell me 1 mole is 2 moles. So that information is no longer given. Okay? Because you need to know that. Okay, 9 grams of oxygen, well, that's actually given information. We have to start with something. In parentheses, 16 grams of oxygen equals 1 mole of oxygen, which, by the way, is wrong for the record, but let's ignore that. Where is that conversion factor found? Where do we find the conversion between grams and moles? Periodic table. We'd have to look that up. So you know that now, so that's not given. In fact, you know it correct, and what I gave was incorrect. Okay? Last one, 18 grams of water equals 1 mole of water. Where do you find that? Periodic table, so that also disappears. Okay? So what are you left with that you are now responsible for being able to solve? 9 grams of oxygen gas are reacted with excess hydrogen gas. Then how many grams of water are produced? Okay. That single question gives you enough information to realize you are reacting hydrogen with oxygen to produce water. Based off of that, you know that hydrogen is balanced, but oxygen is not. So I would have to scale up. I need 2 hydrogens, 2 waters. I now have the balanced chemical equation. Okay? If I then go through and take a look at the question, maybe I didn't even need the equation. What am I trying to solve for? Grams of water. What am I starting with? Grams of oxygen. I've changed the substance, so I have to do a conversion. Okay, at least one. So as I set this up, I could say, well, I need to get rid of grams of oxygen and I need grams of water. Is that a valid conversion? Okay, this is not valid because the only way to convert a substance is through a chemical equation, and the chemical equation tells us the count, the number of those things. So I can't do that conversion factor. Instead, I'll have to do the grams of oxygen to moles of oxygen. Now that I'm in the moles of oxygen, that's a count unit. The count unit allows me to convert substances. I can convert my moles of oxygen into moles of water. Where do I find that conversion? This is the chemical equation. Where did I get the grams and moles? Periodic table. I still don't have my answer yet. I need to get rid of moles of H2O, and I want grams of H2O. Where do I find that conversion? Periodic table. Okay. All of that information is stuff that you have to seek out and you have to find. Okay. You have to know where to find it. That takes practice. We've talked about where all that information is found. You now have to look for it, recognize that you can find it, and then do those calculations. Do that practice. Kind of make sense? Okay. So we did all that. Those are easy, so let's get rid of those. Let's look a little bit at solubility, because we don't have a whole lot else to talk about on this. Water and solubility, virtually all of our reactions are done in aqueous solutions. Why do we do them in aqueous solutions? Okay. If I try and mix salt and have salt react with, say, silver, okay, silver ion, they can react with each other, but the only way they interact is when they actually physically touch each other. Okay. So if we look at how you interact with the outside world right now, how well are you doing? How many people are outside this room? Okay. No, literally, how many people are on the other side of that wall? They're like 10 feet away from you. How can you not know? You can't see them. Why not? There's a physical barrier preventing you from seeing them. When you run a chemical reaction, much is the same. Okay? If I try and react a solid with a gas, the only place where those two particles can interact is on that interface. What about all the solid particles inside the solid? There's now a wall of the other particles preventing them from reacting. So if I want to speed that interaction, what should I do? Get rid of the wall. I will do that by taking all of my reactants, my reagents, and get them all into the same phase. I could put them all into the gas phase, but that then means we could potentially breathe them in. That's not so good. Okay? That's not healthy to be breathing gaseous silver. Okay? Believe it or not, you don't want to do that. okay, for multiple reasons. Right? So what do? We dissolve them in water. Once dissolved in water, now each of those species is free-floating. Each molecule has the ability to interact, every single one. That increases the rate of the reaction. And for those of you saying, well, why do I care about that? Okay, what does that mean if the reaction goes faster? Less time. Less time where? In the lab. The moment you walk into lab, what's the first thing going through your head? When can I get out? If all of our reactions took forever, you won't get out of lab. That's why we put it in solution, so that so we can get those reactions happening faster, so that we can get out of lab faster. So when we're looking at water as a solvent, it's our base solvent. It helps to dissolve our compounds. We see these reference things called hydrogen bonds. Those are not bonds. Okay? I don't care who tells you that those are bonds. They're wrong. They're not bonds. It is probably the worst way to name things ever. It is not a chemical bond. Okay? It is an intermolecular force that we'll discuss later in the semester. Okay? So what ends up happening is that water comes along and it interacts with our compounds. We end up breaking the forces holding our compound together in favor for interactions with the water. Okay? And so that's dependent on this thing known as forces. We haven't talked about forces yet, so don't stress behind it. Okay? But let's think about the other part of this. We had to break the interactions there. Have we broken interactions in a solid before? Yeah, we have, actually. What solids have we broken, and how did we do it? There were a couple groups doing the copper or the hydrate lab where they were removing the water from the hydrate and they saw a liquid. What did they do to get a liquid? Because that was a solid that we started with, right? How did they get a liquid?
Introduce heat.
They heated the crap out of it. You provide enough energy that what did you do? You broke all of those bonds. You broke all of those forces. Okay? So solubility does the same thing. It breaks the forces. So what might be something that tracks with solubility? Heat. The hotter a substance gets, the more likely it will dissolve. And so we can look at solubility charts. And if we take a look at this, what happens as we increase the temperature? Come on, pen. As we increase the temperature, what happens to our solubility? The solubility also goes up. Okay? This isn't always true. For instance, if we take a look at the salt, what happened to the salt when we added heat? It looks pretty constant. Right? Didn't really change a whole lot. But most compounds will increase in solubility when you add heat. Salt just doesn't increase a lot. Sugar increases a lot. Okay? So we could go through, whoops, let's ignore that one for the moment. We could also use these terms unsaturated, saturated, supersaturated. Okay? What is that referencing? If I take 100 milliliters of water and I dissolve 200 grams of sugar in it at roughly room temperature, that is now the maximum amount of sugar that can dissolve. That's why we have the line. So that is now a saturated solution. What if at 20 degrees Celsius I dissolved only 150 grams? Well, that means I'd be down here. Everybody see that? What does that mean? Could I dissolve more? Yeah. So I'm now unsaturated. I haven't fully filled it with sugar. So I'm actually lower than the saturation limit. Okay? What if, for some reason, at 20 degrees Celsius, I have 300 grams of sugar? I've now put more sugar in that sample than is physically possible. What does that mean? I'm supersaturated. Okay? I've exceeded that limit. Okay? We can take advantage of that with changing temperatures to do a variety of fun little tricks and traps, but it's not that big a deal. I just want you to be able to acknowledge what those things are. Okay? What we see in this curve is that if we look as a general trend, as we increase temperature, what happens to our solubility? It increases almost universally. Okay? We get a few weird exceptions. Sodium chloride, if you look, salt, is actually increasing, just not a lot. We get this cesium sulfate that actually decreases. Okay? There's all sorts of weird stuff out there. That happens to be one of them. As a general trend, it increases in solubility because you're breaking those forces. Okay? That is where we'll end today. After our solubility curves, we will pick up with solutions and how to measure them, which, believe it or not, is another conversion factor on Tuesday.